So I made a falling sand game, and I made a video about it. And that video was funny, but it wasn't very good at actually explaining why I'm smart and very hireable for making something like this. So I've added a bunch more features to it, and this video will be explaining what a falling sand game is in hopefully not a boring way. Cool, so what is a falling sand game? Well, a falling sand game is a cellular automata simulation. You big dummy, come on, why didn't you know that? No, okay, but really what is a cellular automata simulation? Well, a quick Google search gives this as a definition. A cellular automata, CA, is a collection of cells arranged in a grid of a specified shape, such that each cell changes state as a function of time according to a defined set of rules driven by the states of neighboring cells. Okay, what does that mean? Well, let's break it down into squares. Each square is a cell, and each cell is one type of thing. And each cell can do things because other cells are next to it. So let's say we have one cell that contains water and a cell of lava comes into contact with it. Well, then I can program it so that when that happens, the cell of water turns into steam. And I did. And like a lot of other stuff.
How did this happen?
Well, first we need to start with a big square of smaller squares, right? Well, in Java, lists with lists in them are called a matrix. So we create a class that will be what those materials are. I named it MasterPixel, which is a great name, by the way, because it makes it super hard to differentiate between actual pixels on a screen and the MasterPixel class when I'm talking about how I set up the scaling on the screen. Anyway, so we make a matrix of MasterPixels. Boom. Beautiful. Now we have a matrix of things that do nothing right now. So now we got to make them not do that. A great place to start would be to, make it display a screen. Well, there are many modules using Java that will help you do that. So what we do is set the screen to the number of pixels wide and tall as our matrix is. So if our matrix is 100 by 100, the screen should be 100 by 100 pixels. But that's quite small. So what we should do is increase the size of our screen by either making each cell take up more pixels or by making the matrix more pixels wide. Alright, so now we have a screen that's just the amount wide our matrix is. So right now, there's no correlation between the screen and the matrix beyond just the size. But a nifty thing we can do is we can use the tool of this module to draw on the screen. So what we can do is give the MasterPixel class the coordinates of itself within the matrix. Then we can loop through the matrix, read those coordinates, and using math, we can tell it where to draw. Depending on how big the cells are in correlation to the screen's pixels is how far we tell it to move before drawing the next square. So, if each cell is 2 pixels wide, it needs to draw a 2 by 2 square of pixels. Then, starting from the third pixel, draw another 2 by 2 square, and so on and so on. When it gets to the end of the matrix, it restarts on a new row from the third pixel down. We put this on the loop, and boom, we have a functioning screen that still does nothing. So now let's just make it do something really, really simple. What we need to do is make it so that the pixel in the middle is a different color. Amazing. Revolutionary, even. Great. Now let's make it so that if the cell has a color that's black, it changes the color below it to the color that it is and the space that it is to black, creating the illusion of movement. We can do this by giving the cell the access to the class that has the matrix in it. This means that any individual cell can access all other cells on the screen, and by minusing or adding to the cell's coordinates, it can check the coordinates of the cells next to it. Capital. So this is great and all, but how do we go from this to this? Well, let's start organizing, because this can get complex fast. Firstly, let's make it so that all actions are defined in the master pixel class. Then we have subclasses to that class, and each subclass gives a general outline of what the class does by changing how it's rendered each frame. Then we make subclasses of the subclasses, changing things like color and other properties. Cool. Now we can create a subclass, change some basic properties, and make a new material. Now, I have glossed over quite a bit here. The main points being how we render each pixel. So, we had the example earlier of looping through the matrix and drawing each cell. Well, when we loop through each cell, we can also render them. This means that each time we land on that cell while scanning, we go through the process that it needs to go through in order to simulate itself. This can be accomplished by having every cell run the render function. Now, we leave the function in the master pixel class empty, but we can make the subclasses override that and give an outline of what those classes of pixels should do. So, this way, there is no rendering of an empty cell, but there is a rendering of a cell where there's actually something in it. The liquid class has several things outlined in it that should be done in a certain order each time it's rendered. Let's give an example of a water cell. The screen scans from top to bottom, and when it hits the water cell, it checks if the cell below it is the master pixel class. The master pixel class, for all intents and purposes, can be considered to be an empty cell. This is because it contains no special information and its color is a solid black. If there is no cell, it moves the water cell down. Now, funny enough, it's less moving and more recreating itself in another location while deleting itself from where it was. Anyway, so it moves down one. Amazing. Except not. Because now, when the scan reaches the second row, it's going to interact with that cell again, making it run its functions again, moving it down again. It does this over and over as the water cell moves down, making it move from the top of the screen to the bottom of the screen in one frame. So how do we fix this? Well, we can give the master pixel class a parameter that it can check on and off if it has done something. This is done when the cell performs an action. It tells itself it has done something, and the next time that the screen loops around, it does not need to render that cell again because it has already done something that frame. Great, now we have a pixel that moves down each frame. But what about moving left and right? Well, using the same logic, we can make the water pixel move back and forth. This can be done by checking if there is an open cell to the left or right, depending on a random number, and if so, it moves itself there. Now we can have the liquid that falls and kind of shimmers on the surface of something. We can take this concept and extrapolate it into many different things. For instance, sand could be a very similar simulation where it checks if there's an empty cell under it and falls. And if there's no empty cell under it, it checks the bottom left and the bottom right and moves there if those cells are open. So, making this run 60 times a second, we can create a cell that looks and acts like water or sand. So you get the idea of how basic movement on this works. Now let's get to the more complex stuff. You might have noticed this earlier in the footage, but the cells are able to fall faster than just one cell at a time. This is because I've added velocity into the simulation. When a pixel has nothing under it, it moves down and adds up velocity. The higher the velocity number is, the faster it starts to move. So it starts to run a loop instead of just processing once. And it loops the number of times the velocity is, checking if there's an empty cell underneath it and moving it down if there is. This makes it so that things can gain velocity as they fall. Another feature that's very important is how reactions occur. I made this happen by first creating a class that allows me to concisely input how I want any cell to react with any cell in its vicinity. I'll go over how this works. So let's call the cell that's checking the interactions with the other cells OmniCell. So the OmniCell can look at the cells beside it and decide if it needs to interact with any of them. The way the recipes in the code are added is by adding an instance of the recipe class to a list in the cell. I can control what cell the OmniCell needs to be next to react, what cell the cells next to the OmniCell will change into, what cells the OmniCell will change into when coming into contact with another cell. This can just be done so that it doesn't change into any other cell, by the way. The percentage chance of the reaction occurring at all, and the size of the cells changing, so we can affect more than just one cell at a time. So each time a cell is rendered, it loops through all the recipes that it has and checks if the cells beside it are part of its recipes. If it is, it plays out as defined in the recipe class. Funny enough, there's actually a huge optimization I could add here if I ever got around to it, which is having a list be created of all the different types of cells that are currently being rendered and only looping through the recipes that contain a cell that's on the screen. So like lava, for example, has a lot of recipes. Instead of looping through all of them, I could just have it loop through the ones that have a recipe for cells that are actually on the screen. But, I didn't add that. Anyway, another more complex mechanic I will cover is explosions. Now, this could have just been added simply by making it so that when something explodes, a circle is made around that point, replacing all the cells not strong enough. But this would allow it so that the explosion could travel through walls of a material that was strong enough to withstand the explosion. So instead, I had to make it like way more complex. Okay. So, let's get this idea. What I need is for the explosion to move out in a straight line, and if it hits a hard material, then stop. And then it needs to do this in a circle to create the effect of an explosion that can be blocked by harder materials. To do this, we need to use trigonometry. This is the branch of mathematics that is really useful in game design, as it allows you to draw a straight line from one point to another using a triangle. I made the class that calculates this and adds each of the points in the line to a list so that another function can loop over that list. Great, so we have this class that calculates the line, gives us the cells that needs to be updated, and we can loop through this so that it draws a line from the center of the circle to the outer circle and does this over and over and over, drawing from the center to the perimeter of the circle until the entire circle is drawn, replacing all the pixels with the appropriate explosion effect. Except no. If you do it this way, you actually run into a problem where some cells are not in the direct line of any of the lines from the center to the perimeter of the circle. So what you actually have to do is path out the line to the perimeter of a square and just count the amount of cells it replaces as it goes along. You can add the coordinates of any of the cells that have been replaced to a list so that if the lines overlay, then you don't have to replace the cells twice and it will just skip that. So, as the line goes out, the cells will change, and this makes it so that within the circle of the explosion, 100% of the cells are updated, and it's done in a way so that materials can block the explosions. Anyway, as I mentioned in the beginning of my last video, this project is actually how I ended up learning Java. It's been both very challenging and fun to work with. I like a lot of the ways Java works, and object-oriented programming is a fun thing to use. I feel like a lot of the tutorials I saw suggested that I create way more classes than I ever needed. I ended up finding what I felt like was a happy balance in the end. This project was always nostalgia-fueled for me. Seeing how I grew up playing these games, it's cool to see how I went from being 9 years old playing these games on my computer that took 20 minutes to start, to going to making one myself. Hopefully this video managed to keep your interest. It took a long time to write the script, create the visuals, and of course make the project. You can find my resume on skataskills.com.